All right, good morning, everybody. My goal of this is to hit some different energy ideas because I know some of us are getting some of it, we're missing some of it. So that's the goal of this. So look ahead and see which problems you need. We're going to do them in order. So we're going to start with just energy 101. There we go. So first question is, we've got ourselves a 3 kilogram ball. We drop it from 12 meters up. And then we're going to talk about all the different ways you would see this problem. So we have a 3 kilogram ball, and it's going to be 12 meters up, and it's going to fall. And the question is, how fast is it moving when it hits? Okay, so what we do is we start with what form of energy does it have at the top? Well, at the top, it has gravitational energy because it has height that's going to be changing. At the bottom, it's moving, so it has kinetic, but it doesn't have any height left. And so since it doesn't say that there's friction, since it doesn't say there's any air resistance, we can set those equal. So we could say gravitational energy equals kinetic, that those are going to transfer into each other. So gravitational is mgh equals 1/2 mv squared. Now, I could cancel out the m's, but they give me an m, so I can totally plug it in. So let's just plug it in. G is 10, the height is 12, 1/2 mass v squared. I'm going to get numbers in all of this so you can make sure you're doing it right too. So 3 times 10 times 12 divided by 1/2 square root. I get 15.5. So I want to talk about a couple things. One, I know when we've done this in class, I see a lot of people doing this, which guess what? Works just fine, because if it falls straight down, the acceleration is -10 meters per second squared. The initial velocity is 0. It falls -12 meters because it falls and loses height. We don't want time, we don't know final. So totally yes. So those of you that have been doing that, keep doing that. I think it's great. But I want to show you the limitations of that. Let's say the ball goes down a ramp, and the ramp is 12 meters tall. I'm going to cross this out, not because it's wrong, but I can't use that for when it's on a ramp. I also can't use that for if it does this. And I'm like, well, how fast is it going at the bottom of it? Oh, there's a little loop-de-loop and it gets to the bottom. How fast is it going? I can't use that because it doesn't always accelerate at -10 meters per second squared. But I can use energy because it starts with the height, it ends with the velocity, and so I can use that. So the energy, yes, for that one, you can also use that, yes. But the limitations of it is energy works with all three of these here. I meant to have all these arrows go here. Energy works with all of those to get them. So I want to kind of see the limitations, but also kind of, I don't want you to say, oh, I can't use that anymore. You can, but you can only use it if it's going straight down. All right, I'm going to erase this. And what we're going to do is we're going to, I thought I was erasing that. Let's try that one more time. Here we go. So now let's scroll down. So now we're going to go to the next type, is where we throw a ball off a table. And I'm going to make some space here because we've done these with projectiles. So now we're going to try to think, okay, well, how do I do projectile stuff with it? And well, okay, let's start by saying what we got. We've got ourselves a ball, 2 kilogram ball, throw it sideways off a table. So let's just draw a picture. So we have a table, we chuck a ball off of it. Okay. So what we do is we think, what type of energy does it have at the beginning? Well, at the beginning, it has height, and it's moving at the top. At the bottom, it's just moving. So at the top, it has height that it's going to transfer, and it's moving, so it has kinetic also. So I've got mgh plus 1/2 mv squared equals 1/2 mv squared. So 2 times 10 times the height of my table plus 1/2 to speed of the ball equals 1/2 mass v squared. Now notice, these all have m's in them, so I could just delete the m's. I totally could do that. But since we have it, I'm just going to plug it in. Okay. So is that hopefully you're not yelling at me right now. If you want to cancel this out, you can. But I think I've been noticing as we're doing work together, so when people cancel out the m, sometimes they forget the g. So be careful about that. That g is still there, it's still 10. So So we got 220, 6, 120. Hope it's okay that I'm sharing kind of common mistakes I've seen across all of our classes and all of our students, because they're very normal. I see them all the time. So just want you to know that. So we got 184 equals v squared. No clue what that is. All right, square, oh, you know I don't want a graph. Square root of 184, 13.5. And guys, you go through the video today. If you see anything wrong, please just let me know. That's how fast it hits. How do we know it's right? It's bigger than 8. And it's not obnoxiously big. Okay, so it's about 13.5. It's about good. How much time? So this is review. Okay, this is I want to connect what we're doing here to what we did with projectiles. So if you're like, I don't want to do projectiles right now, that's fine. Go to the next problem. But how much time does it take to hit the ground? So if we want time, energy does not touch time. Instead, I have to go back and, oh, that was a bad joke I almost said. We have to go back in time and review projectiles. So projectiles, horizontal has velocity, displacement, and time. Vertical has initial, final, acceleration, displacement, and sorry, next problem, time. Okay. Acceleration is -10. Since I shoot it off of a table, the initial velocity vertically is 0. I launch it horizontally at 8. The table is 6 meters tall, so it falls 6 meters. It accelerates at -10. We don't know. The final velocity is only the vertical, so I cannot plug 13.5 there. Actually, I'm actually happy I'm ready. Yeah. So the question is, how much time does it take? So I'm going to use the equation with no v final. No v final, no v final. That's the last one. So delta x equals VIT plus 1/2 AT squared. I hope this is helping. I hope this is a good review, okay? The fact that you're listening to this, rock on, okay? So it falls -6 meters, initial 0, because it's going horizontal, so it's not gaining altitude or losing, so it's just getting shot sideways, so there's no initial velocity vertically here, okay? It is moving at 8 meters per second, though. So 1/2 AT squared. So we get -6 equals -5 t squared. So we get t squared equals 6/5. And it's positive now. I'm going to get square root, just so we get a number. Square root 6/5, 1.1. That is the time it takes. Okay. This is bonus. Please do not think this is absolutely necessary, but I want to just drive something home. So if I do the first equation, v final equals v initial plus AT. So I'm just going to look at the vertical here, only the vertical. So v final equals v initial plus -10 times 1.1. So v final is -11. Mr. Schmear, oh, that's 13.5. Oh, let's get me out of there then. Watch this. Vertically, it's going -11 meters per second. Horizontally, it's going 8 meters per second. So by using energy, we avoided having this conversation. Because look at this. Right here. What could I do? I could do a squared plus b squared equals c squared. So I get 11 squared plus 8 squared and square root, and I get 13.6. Okay, so we do get the right answer, but when we break it up into horizontal and vertical, that number we get for v final is not the overall v final because it's going sideways and vertically. So that might have been overkill, but solving for time, that's a question that we get. The next question is, if you dropped a ball, which one would hit first? So if you dropped a ball and throw a ball, they still hit at the same time because vertically they're still falling the same. So if you launch it sideways and drop a ball at the same time, they'll hit the ground at the same time. All right. And as always, guys, if you're doing these and you're like still not clicking, just let me know. Okay, happy to work with you. Maybe there's a different way to explain it. Maybe I got it wrong. Just let me know. So now we're going to do 2 roller coaster problems. So the first one is a roller coaster starts at the top of a 20-meter tall hill, and if it starts from rest. So this is like our pivots. That roller coaster is going really, really slow at the top, and at the bottom it's going really fast. So I'm going to take this. So we got a roller coaster, 20 meters tall. Okay. And it starts at rest. So let's talk about what type of energy does it have at the top, and what type of energy does it have at the bottom. It's top, it's got gravitational energy because it's got height that it's going to transfer. It's not moving, so it doesn't have any kinetic. At the bottom, though, it's moving. It's cooking. So I can set those equal. So mgh equals 1/2 mv squared. Oh, I didn't give you the mass of the roller coaster. See how the mass is on both sides? You can cancel out. So I'm off of g times h equals 1/2 v squared. So we get v squared equals 400. So we get a velocity at the bottom of 20 meters per second. That just happens to be the same as the height. Please do not. Okay, but square root of 400 is 20 meters. Yep, is 20 meters per second. So notice that looks like that first problem we did, because even though it took this crazy path, all it did was drop. Okay, so there's that guy. But I know what you're saying, Shmear, but I've been seeing these ones where, let's get this on the next page. Yeah. So roller coaster, let's make sure we got space. Roller coaster is on a 60-meter tall hill moving at 11. So let's just draw it out. Oh, I forgot to give the mass again. Okay, so we got a 60-meter tall hill, and it's moving at 11. I always draw an arrow just to kind of drive it home, like we're moving. It goes all the way to the bottom. How fast is it going? That's my goal, okay? So at the top, I've got gravitational, and I'm also moving. So I also have kinetic. At the bottom, I just have kinetic. So I can set those equal because there's no air resistance, there's no friction that they're talking about, so I can set them equal. So I can say mgh plus 1/2 mv squared at the top. So those 2 types of energy are happening at the top. I'm trying to look at you guys. Sorry for looking away. And then at the bottom is just kinetic. So 1/2 mv squared. Since these all have m's, I can just cancel them out. So 10 times my height plus 1/2 my velocity at the top. So we get, was that 600 plus 60.5 equals 1/2 of v squared. So 660.5 equals 1/2 of v squared. Get v squared equals, oh boy. So we got times 2. So it's 1321. And to get my v at the end, I square root. I get 36. Pretty fast. It's about 70 miles an hour. So the key to this, so just review and recapping this question. Start by looking at what forms of energy do I have. If I have height that changes, I have gravitational. If I have motion, I have kinetic. Okay, and at the bottom, I don't have any height left. Before we do the next problem, I want to drive something home for bonus. What if it's the same problem? It's the same problem as the last one, okay? But you start at 80 meters, and the bottom, I'm gonna sneeze, is 20 meters off the ground, okay? I wanna think about this guy. So we've got same problem as the last one. Let me scroll down so I can see the problem I just wrote. So instead of starting at 60, we're gonna start at 80. Oh no, Shmear. Right, so we're gonna start at 80. But now the bottom of the hill is gonna be at 20 meters. But I'm gonna start at, so here's 20 meters, right? I'm gonna start at 80 meters. Okay. If we know that this is the lowest point we're going to go to, I can call that 0. So if that's 0 at 20 meters, because I'm not going to go any lower anymore, how high is it? It is still 60 meters from its lowest point. And so I can use everything that I did here. Even though I started at 80 and ended at 20, I changed 60. And so that's the key on these problems. So that's the one wrench I was thinking that you could see a problem that might kind of mess with you a little bit is if they give you start and ending heights, and if you just subtract those, you could just use that one height. Okay. Oh, there it is. There's the work. So up here, so it says gravitational plus kinetic and only kinetic at the bottom. Because if you use 20, right, you got gravitational at the end. But if you say that that's 0, that's my bottom, then you don't have to use the 20. You can just use the 60, and it's exactly the same setup because you changed 60 meters. I want to do one last one with number 4. Bonus number 4 again. It's exactly the same problem. So I'm going to start at 80 meters. I'm going to end at 20 meters, and it goes down below it, all the way to the ground. I can set this up and say, that's my 0. And I could say this says gravitational, same problem still, 4, and it's moving, and kinetic. And when it gets here, I can say it just has kinetic if I call that 0. So I would say mg, I don't say the total height, I only say the height that it changes, 60 plus 1/2 m11 squared. So in this problem, if I start at 80, I go all the way down to the ground, but I come back to 20, I can still use 60, and then I'll just set that equal to 1/2 mv squared plus no gravitational, because I would just be saying, hey, that's the bottom, okay? You can still do it this way. You could still say mg 80 plus 1/2 mv squared equals 1/2 mv squared plus mg. I got 20 left, right? You could say I got 80, I got 20, right? But watch what happens when you subtract that over. I get mg 80 minus mg 20 is mg 60. You end up with the same exact thing. So I really hope that last conversation helped you and didn't hurt you. So if it hurt you, I'm so sorry. Let me know, okay? But if I made things worse, just rewind, okay? We're gonna get on to the next problem. Man, that sidebar, I'm really doubting it. Hopefully help one of you. Okay, next one's dealing with power. This is kind of a tricky one, so I just want to just give you exposure and a chance to kind of digest this. So make sure you try to set this up. So the question asks about power. Since they ask about power, I'm going to start with just big ideas. Power is change in energy over change in time. Well, they gave me, oh, there it is, time. They gave me time. I'm good. Change in energy. Let's think about that. Change in energy is final energy minus initial energy. Okay. Well, at the beginning, it's moving, and at the end, it's moving. So the final energy is kinetic energy because it's moving, and the initial energy is kinetic energy because it's moving. So my change in energy involves both of those. So power is kinetic energy final minus kinetic energy initial all over time. Now, we did in class, we just said, hey, you raised it, and you got there. And so you just had mgh. Or, hey, we pushed it from rest, so it just ended with kinetic energy because we started with an initial of 0. But if I wanted to give you exposure to this problem, or what if we start with speed? So kinetic energy final minus initial, 1/2 mv squared minus 1/2 mv squared all over time. It's very important. I can't cancel out m's now because it's not in everything. It's not in the bottom. If it was in the bottom, I could cancel them out, but it's not. So 1/2 800 times final speed squared minus 1/2 800 times initial speed squared all over time. I'm gonna plug this in my calculator. I'm gonna do the top first. Half times 800 times 30 squared minus half times 800 times 10 squared. I just get a number, 320,000. All over 3. So that top unit is joules and the bottom unit is seconds. So I'm gonna divide that by 3. I get 106, get out of here. So 107,000 watts. Okay. Which is about 142 horsepower. That's kind of just like a car, kind of like your normal sedan. So I tried to make a problem that was actually accurate. So that's what power is. It's in watts, 107,000 watts. So just like those things in your wall, those are light bulbs. Cool. I want to do one more on here. I'll type it on here so people know it's actually existing. So this is number 6. Which is going fastest? This is, believe it or not, this is actually a really interesting question. But we've got a slide, goes steep like this. Another slide goes shallow. Another slide is a loop-de-loop. And another one, the slide just goes straight down. Okay. And the question is, which one's going fastest? So I'm going to have like a box or a car or something at the top. Which one's going fastest at the bottom? All right, answer. If they all have the same change in height, which I tried to draw them the same, they'll all start with gravitational. And they'll all end with kinetic. And since that change in height is the same, those will all be the same. So gravitational equals kinetic. And if I solve that, mgh equals 1/2 mv squared, I'll get all the same v's because all the same h's. Okay, that's the power of energy. Okay, so all of them will have the exact same speed. The question I did not ask is time. Which of these will take the least amount of time? This guy. Because it's got the shortest path, it's the direct path. It has an acceleration of -10. The other ones don't. So if we're talking time, this guy has the least amount of time. So those ideas that we have around time, so sometimes we say time, we say fastest. They are all the exact same fastness, which is speed. They have the same speed, but that last one does take the least amount of time. All their speeds are the same at the end, but the times are different. All right, guys. Hopefully this helped reviewing the ideas. Cool. Keep sending questions. Happy to help. Talk to you guys. Where's the stop button? Found it. Thanks for tuning in.